In this tutorial, we will learn how to define ventilation flows in VOLTRA. We will continue working with the same project file used in the previous tutorial. If needed, you can download the project files for this session from the link provided in the comments. For additional background, refer to section B.23 of the VOLTRA manual, which explains ventilation flows in detail. To begin, we will add a ventilation flow of 100 air changes per hour inside the cavity between the wall and the glass unit. In VOLTRA, ventilation paths are created using the Physibel color types BC-free and BC-free-S. These color types can interact with each other even if they are not adjacent in the model. The origin of a ventilation flow path may also be defined using BC-simple or BC-sky. In this example, we consider forced convection inside the cavity. The cavity currently has color 193. Open the colors window and set the standard for this color to nihil. This allows us to manually define the convective heat transfer coefficient. Enter a value of 2.5 watts per square meter Kelvin. Next, calculate the required airflow rate. The cavity has a depth of 0.1 meters, with a height and width of 1 meter each. This gives a total volume of 0.1 cubic meters. With an air change rate of 100 per hour, the resulting airflow rate is 0.00277 cubic meters per second. We will use 0.0027 cubic meters per second in the model. From the Edit menu, choose Ventilation Flows. Insert a new row. Define a ventilation flow from color 170, representing the exterior, to color 193, representing the cavity. Enter 0.0027 as the airflow rate. It is not necessary to define a separate airflow from the cavity back to the exterior, as the software automatically assumes that the incoming air exits at the same rate. Click on Calculate to run the analysis. We can compare this result of temperature inside the cavity with ventilation versus without ventilation. To obtain a more detailed temperature distribution inside the cavity, we will subdivide it into 4 parts. This approach creates 4 separate convective nodes, allowing the airflow to pass from one node to the next. This provides a more precise temperature profile along the cavity height. First, split the grid in the z direction into 4 equal parts. Then select the block with color 193 and copy it 3 times. Assign new colors 194, 195, and 196 to the additional sections. Ensure that the corresponding grid numbers are also assigned correctly. In the Colors window, copy the properties of color 193. And paste them into colors 194, 195, and 196, so that all sections have identical thermal properties. Return to the Ventilation Flows window and insert 3 additional rows. Define ventilation paths from 193 to 194. From 194 to 195. And from 195 to 196. Assign the same airflow rate of 0.0027 cubic meters per second to each path. In the Report Definition window, add 4 new rows for colors 193 to 196. And assign theta A as the output for each time step. Then rerun the calculation. Once the simulation is complete, export the temperature values within the cavities to Excel. Plot these values to visualize how temperature varies along the cavity height, highlighting the formation of a temperature gradient caused by upward airflow. Ventilation flow rates can also be defined as time-dependent functions. To demonstrate this, create a new function with the reference v01. You may link this function to an external text file containing a list of numerical values representing airflow rates over time. Alternatively, you can link to a predefined mathematical function, such as a positive sign function. Enter the parameters as required. To better visualize the function graph, open the Functions menu and select Y-scale. Choose fixed values and set the maximum value to 0.0027. This makes the variation in airflow easier to interpret. Then link the function to the ventilation path by entering the reference V01 in the flow rate field. Click Calculate once more to run the time-dependent analysis. After the simulation finishes, you can plot the temperature profile within the cavity for each time step and observe how the temperature responds to changing airflow rates. This example's considered forced convection. A procedure to introduce natural convection in the cavity is available in the knowledge base, under second VOLTRA tutorial. Finally, note that ventilation flows in VOLTRA are not limited to air. They can also represent other fluids, such as water. For example, in the Physibel knowledge base document C12 floor heating. Ventilation flow is used to model heat transfer from hot water flowing through pipes. When modeling fluids other than air, it is essential to input the correct density and specific heat capacity, since the default values correspond to air. Thank you for watching. See you in the next tutorial.